Two functions adding. And then you break it into two. We only have one C in the end in the final answer. Why is that? Why are there two C's? That makes sense.
A couple different ways you can think about. Here's what I prefer. When we're doing an antiderivative, we're imagining that, hey, we've got f prime in our hands, and we're trying to find what f was, right? So f was some function, but it could have had plus 10 on the end.
Yeah.
And then when we took the derivative, that 10 disappeared. So when we're going backwards, we just really need to account for maybe one extra plus.
That makes sense.
Does that kind of make sense?
Yeah, that makes sense. Thank you.
Like you wouldn't have an f function that said something like this. Your function for f would not have been written as, say, f of x equals, just a simple example, 4x cubed plus 3 plus 2x squared plus 5 plus x. Yeah. They wouldn't have written it that way, right? They would have just already combined these. So when we do the antiderivative, we can just put 1. Is that
Thank you.
2 points?
Can we go over 7?
Yes.
Yes.
Is this 7?
Yeah.
Anyone have a questions at that point? So don't talk now. Does anyone have a question at this point? Do you want me to talk more about it? Okay, all eyes on the board, everybody. Everybody looking? Okay, when I first introduced U substitution, I tried hard to kind of prep you for the idea that I was teaching you a step-by-step process to help give you some structure to U substitution. But once you get good at U substitution, you can actually use it in more flexible ways. So I'm going to show you on this problem the way I would actually do it, which is a little different than the kind of formal method I taught you. If you can make sense now that you've done the formal method a bit, if you'll make sense of this little shortcut method, you'll suddenly find U substitution quite a bit easier. Good? Okay. When I look at it, my first thought is there is no rule. Second thought, well, I do have two things multiplying, so that looks good. Next thing I do is I just kind of play around with it. I think, well, if I had x squared be u, the derivative would be 2x. But 2x isn't this, so that doesn't seem good. But if I choose u to be x cubed plus 1, the derivative is 3x squared. That is this. So I just jump right into u substitution by writing over here u equal x cubed plus 1. I don't worry about anything else. Then I just take the derivative of both sides. I multiply the dx across. And I move the constant. So that's the way I typically actually solve a problem without really thinking much deeper. So, questions to that? Elijah?
So when you gave us U substitution, you didn't give us like, are you saying that the square root is just the 1/2 power? That makes sense to something.
No worries, 2 points. What else? Okay, another big warning. So everybody look at me again. Look at me. Okay, I've been helping a fair number of people, before school, after school, etc. And the same thing keeps happening over and over again. Students are randomly making replacements. Like really no reason whatsoever. They just say, well, I think I'm supposed to take away dx and put du in place. And I'm like, why? what gives you the right to take away dx and put du in place? You only make substitutions when equal says you can make substitutions. So pay close attention to the equal sign. So from this line to this line, I've got to make sure that whatever I write next is exactly the same. So I put a 1/2, 0 to 2. Now I'm going to say, instead of writing x cubed plus 1, I'll just write u. Instead of writing square root, I'll write 1/2 power. That's totally legal because those are legal replacements. They're not just random memories of, well, this other problem I put du's for some reason. I don't know why, but so make sure you make legal replacements. Question? So now I've got an x squared dx left. But right here I have a replacement for that. The 1/3 is a multiplying constant, so it can come out. Question? You need me to do anything again? You don't need me to talk through anything again? Cool. When you are doing a integral with u substitution, please make sure you forget about x and never go back. You just change everything to u. That way you'll be able to get every question that involves u substitution correct on the AP test. If you don't use that method, you'll get 3 out of 4 of them right, but the 4th one you'll lose points because they'll structure the problem in such a way that you have to use this method. So you change to u, don't go back. So I want to change these limits, so I come over here. Again, I'm simply using the equal sign. So u is equal to, the upper limit is 2 for x. So that's 9. The lower limit is x equals 0. Questions? Please.
So does the 1/6 stay out even though that is part of the 1/2 from the original limits of the average?
So anytime you have a multiplying constant, it can always come out of the integral.
Right, so nothing changes when you do that.
Nothing changes, no.
And so that would still be the average of that, even though it's not from 9 to 1, the limit, it's like it's not.
Yeah, it still ends up being the average of this function here. It's a really good question, from 0 to 2, because everything we've done is just a legal mathematical manipulation. So it's still the same thing, it doesn't look like it anymore, but it is exactly the same. 2 points. Cool. So now we use the fundamental theorem. So we need to think of this as being f prime. And we need to find f. So let's see, the 1/6 is just a constant. F would be u to the 1/2 plus 1 divided by 1/2 plus 1. And we've got to find out how much f changes between 1 and 9. Question? Cool. So we plug away. Dividing by 3/2 is the same as multiplying by 2/3. This reduces to, let's see, that'd be 1, so 1/9. Now we can start plugging stuff in. So we have 9 to the 3/2. Subtract 1/9, 1 to the 3/2. You don't need to repeat any of that. When you have a fractional exponent, remember you've got to take care of both the power and the root. The root is typically easier. Square root of 9 is 3. 3 cubed is 27. One to any power is just 1. Confusion, puzzlement, stress, anger, any other emotions you'd like to express? This chair isn't working, it's just going down as I sit on it. So,
the trick through when a fraction is the power, what do you do again?
no, 2 points. So you've got, basically you have, this is the details, Nathan. When I have 9 raised to the 3/2 power, you can think of that as being the square root of 9 cubed. Or if it's easier, you can think of it as being 9 cubed and then square root. But the top one's typically easier. Anyone else? You know, let's come prepared with a specific question. Please, Rachel.
Can we look at number 13?
Is that right, Rachel?
Yeah.
This one, 2 things being added, I can do them separately. So what I'm going to do is a lot in my head this time. You can do the same. So just think of them separate. I remember, if I'm doing an integral, I'm thinking of this as f prime. I've got to find out. So the 4 being a multiplying constant just tags along, so just write it down. Then you've got x cubed, so the antiderivative of x cubed is x to the 4th over 4. The 6 tags along. X to the 1st antiderivative becomes x squared over 2. So that is my f function right there. And this would have been the f prime that I started with. So now I need to take f and find the value of f at 2, find the value of f at 1, and subtract it. And you want me to talk through that again?
Can you do that again?
Huh? So in pieces, are you okay that the fundamental theorem is telling me that to find this integral, I should think of this as f prime, and I need to find f?
Yes.
Okay with that? Awesome. To find f, I say these two are being added, so I just think of them separately. The 4 being a multiplying constant, I don't really worry about, so I just wrote it down. Then I've got x cubed. So on the green sheet, very first rule says antiderivative of x cubed will become x to the 4th over 4. There's the minus. 6 is a multiplying constant. This is x to the 1st. So first rule on the green sheet says antiderivative of x to the 1st is x to the 2 over 2.
Okay.
So now I have f, I need to plug in the 2 and the 1.
Okay.
Since I'm using the fundamental theorem, which says this. 2 more for Rachel. Anyone else need me to repeat any of that? I can keep going if you need me to, but the rest of it really is just arithmetic.
Yeah.
You good? You want me to keep going?
I'm good.
Okay. I would certainly divide a little bit first. then I just plug it in. Question? Trey?
We do number 12.
So let's do number 12, the shortcut method. So I do see two things being multiplied. I play with it for just a moment. I think, okay, wait a minute. If I were to choose x cubed, the derivative of x cubed is not e to the x to the fourth. So bad choice. Anyone need me to explain the bad choice again? Just wait. So I think, let's try x to the fourth. Derivative of x to the fourth is 4x cubed. That's a perfect match. You need me to talk through why that works. Cool. So come over here. Steps are identical. They don't really ever change. U is equal to x to the fourth. Du dx is 4x cubed. So du times 1/4 is equal to x cubed dx. You need me to just wave if you need me to do that again. Now it's time to start making, we got to change the limits. Let's just go ahead and do that now as well. So u is going to equal, hey, the limits don't change much. They actually don't change at all. So I'm ready to come over here and say, my new limits are 0 and 1. I've got e to the u. And I've got x cubed dx. X cubed dx is 1/4 du. Pull out the constant. I can talk through as much of that as you'd like. Just you have to tell me what part you want me to talk more about. So.
See what I did wrong.
Okay.
Yeah.
No worries.
I think I got it now.
Anybody else? Please, Isaac.
On the top right, when you switch from du dx to 1/4 du, just I don't get how that part works.
No worries. So, are you okay from this line to this line?
Yeah, you take the derivative, right?
Perfect.
Okay.
After that, I'm just going to use some basic algebra. I hate this board. I actually like the board a lot. I just hate when I try to highlight something. Like, did you see what I did? Like, I circled this. Like, I get it's trying to be helpful. I guess I could do this. No, that doesn't help. Like, my thought was maybe I can change the selection, right? Apparently not, so that's annoying. So you're good here, right?
Yeah, I get that.
I will try to stop complaining. Just multiply both sides by dx.
Okay.
If I multiply both sides dx, you tell me what would I write. Like if this has dx multiplied on both sides, what would I have?
You get du
Keep going, Isaac.
equals 4x cubed dx.
Perfect. You okay with that?
Yeah, I get that.
Now I'm going to multiply both sides by 1/4.
Okay.
So what will this side become?
That'll be 1/4 or 1/4 du equals x cubed dx.
You're doing splendid. Does that make sense?
Yeah, no problem.
Perfect. You good?
I got it.
Awesome. I just multiply because I'd rather multiply than divide any day.
Okay.
Division, yeah. Multiplication, fine. So, please, Alice.
Question number 16.
Hold there for a second. Does anyone need me to keep going, or can we quit here? Keep going. So we plug it in. So again, fundamental theorem. This is f prime. We need to find f. But the antiderivative of e to the u is just e to the u. So that was rough. So that's my f. And I need to find f's value at 1 and also 0. So I keep going. So I have 1/4 e to the 1. Subtract 1/4 e to the 0. Okay, please, on the written portion of the test, please stop there. You're done. You get full credit. Multiple choice, I've got to find my answer, so you got to help me. Did they factor? What do they do? Profound silence. They factor. They pull out a 1-4. E to the 1 is just E. E to the 0 is 1. Is that the way it's written, Hadley?
Yep.
2 points. Hadley. Anybody else? Please.
Can we talk about number 14?
Yes. Allison wanted which one?
16.
So one at a time here. Let's do 14 because it's really fast. Okay, I just got done telling Hadley and Isaac I would much rather multiply than divide any day. I think it's just easier mentally to think of. So I don't like thinking of t divided by 2. I like thinking of 1/2 t. Now all you have to do is pick up your green sheet, look at the expanded E rule, done. Please. One moment. Do we need me to show more here? Please,
How does that fit underneath the expanded E rule? Does this have to have, I guess the B can just be 0.
right, the B is simply 0. Good comment, 2 points. No? I've got too many questions running through my head. Somebody wanted this one, that was Mikkel, eh?
Yeah.
Allison, you wanted which one?
16.
Same thing, expanded E rule. I'll number the steps. Please talk to me if you want to speak further about any step. The ending was just a mess because I didn't have the multiple choice answers in front of me, so just took a few weird gyrations to get to the multiple choice answer. For your response, please stop at step 2. Try and see if the chair can work properly.
I'm confused with the 1 4. Oh, is it just 3?
So this is E to the AX plus B. So what's the A? Perfect. What's the B? Good. So you look at the sheet as I talk. So looking at the expanded E rule.
I forgot about the 1 already.
Somebody else? Allison?
Okay, so I get where you plugged in your points, but I don't know where to go. I guess. Never mind, that makes sense. Okay.
Work. 2 points for Allison. Anybody else? Hey, which one? 11. Pay the whole room. No, it's too easy. u is simply x squared plus 2. Same thing again. You would need me to talk more about that. You need me to talk about how I knew the x would be x squared plus 2. Cool. Need to make all my substitutions. We transform to u, we don't go back, so let's change the limits. Need me to talk more about that. It really is just substituting. So now it's the fundamental theorem. So this is my f prime. Therefore, my f function will be u cubed over 3. I need to evaluate my f function at 3 and 2. So that'd be 1/6. We pull out that 3. Question? Wave if you need me to finish, otherwise we'll quit. Anyone come prepared with a different question? Okay, cool. Let's go to the yellow. All right. So on the yellow one, please write down in your notebook. Number 1. We have done this little trick over and over again, so this isn't very new. This can be thought of as two things multiplying. You'd have cosine of x over 1 multiplied by 1 over sine. Using the new trick I taught you today. You could say, well, if I pick this as u, the derivative of the cosine is -1 times the sine, but this is 1 over sine, so that would be a mismatch. Wave if you'd like me to repeat that again. So I could choose this as u, it's totally fine, but the derivative of cosine, let's see, Susie's circle helps. So draw the circle. Sine's the up and down. Cosine's the back and forth. When taking the derivative of the cosine, the result would be negative sine. But this is not negative sine. This is 1 over sine. So choosing u to equal cosine isn't going to help. Just wait if you'd like me to say that again differently. Where does that chart come from? So this is on your green sheet. Oh, okay. This was invented by a student who was having a hard time remembering the positive and negative. Common error. So she noticed a really cool pattern. She said, if I'm doing the unit circle, the sign I'm always thinking would be up and down. That's how I find the sign. So she wrote sine and negative sine, similar for cosine. And then she said, look how cool this is. The derivative of sine is cosine. The derivative of cosine is -1 times the sine. And it just keeps working. If you go anti-clockwise, it's antiderivative. Susie Lind is the student. Susie's circle. So if your name has some sort of catchy geometric shape associated with it, you need to come up with some really cool rule as well. So If you have a hard time thinking up a catchy name, I'll help you with that. Just come up with a cool rule, and that's all I need. So I'm also still waiting for someone. This has been about 9 years since I had Susie in class, maybe 10. So I'm still waiting for someone to donate a nice picture of Susie's circle. See, this is not, Danica did not make this. Danica thought up the idea, and then a generous student named Dallin Ott presented it to me. So it's very nice. Danica's chart by Dallin James Ott. You don't seem that interested. Okay.
Wait, is Danica a student?
Yes.
Oh, what?
That's what everyone always says.
Wait, really?
Oh yeah, I bet people Google Danica's chart and you get
I
did. Like if you go to YouTube, if they can translate what I'm saying, it would finally say Danica's chart. But yeah, Danica is a student. She's in Allison's ward. Yeah.
Really?
Her name is Danica Wright.
It sounds like something from like ancient
Person from the ancient world.
That's what I've been saying.
What's that?
Why did she get her?
No. There, it's right there. That's where it's in. So what Danica did that was very helpful. Would you not agree this is a helpful chart? Yeah. Okay. So what she did is, how this all started is about April. She was in the very first 2 calculus classes I taught, one of the first 2. And she's sitting really right about here. It's after school. She's working very diligently and prepping for the AP test, just like Allison does. No, really, it's true. And I was helping her with something. As I was helping, I noticed not exactly that, but pretty close, right? On her paper. And it took like a half a second to go, that's really helpful. Like, how did you come up with that? And she said, well, I just noticed that over and over again as I work these different AP problems, I keep needing this information to help me kind of remember how the F relates to F prime, etc. And so I just asked her, I said, that I think would help a lot of people. Do you care if I use that in class next year? Oh, no, fine, you go for it. No. So I started using it. I didn't want to, she thought of it, so I call it Danica's chart. And then I think 2 years later, Dallin made me a nice sign, and I've talked to her mother a couple of different things here and there, and she's like, oh yeah, it's really fun. I'll be like in church, and kids will come up to me, and they'll eventually make the connection. You're Danica's mother. They're like, thank you for giving birth. You changed my life. So anyway, yeah, it's much harder. Like, you have to remember the relationships, but the chart organizes the relationships in a nice, easy to remember fashion. And people always say, well, why don't you share it? I'm like, I'll share it to anybody who asks. I don't care, but I don't find other teachers think it's that cool, because they have those relationships so well memorized that they fail to see why it would help someone who doesn't know it yet. You know what I mean? But no, I don't. It's not like I hide it. I'm not really an internet person, so I'm like Snapchatting and things. Anyway, yeah, that's good. I don't know what we're talking about now. But, yeah, Susie's circle isn't quite as famous because it's much more limited in its use, but it's still helpful. So, yeah. Pretty good? Still waiting for the next great student invention I can put on my wall. Always open to ideas. Reese Curtis made me a nice sign that says no it, so I'm going to put that up here. Cool. Here we go. So I don't want to choose cosine, but look how nice this works. If I pick u equals sine of x, the derivative of sine is cosine. Go for it. What are you waiting for, man? Same thing as before. Gets boring after a while, you know.
Skip the whole dx step and just multiply.
What's that? Oh, just skip it, right? Yeah, I get
just
you.
go straight from e to d.
Yeah, I'm with Hadley, man. Just forget all this intermediate stuff. It's too easy. 2 points. I've got to change the limits. Okay, I said something in first period I strongly believe. Oh, 1 second. If you're working a problem and you get to where you have to remember something from the unit circle and you feel nauseous, like you feel sick, you've memorized the circle incorrectly. And I really believe that if you will come work with me before after school for just a few minutes and you'll talk with me, not just watch me, you'll talk, you will be healed. Seriously, you'll never feel sick again from the unit circle. You'll feel sick about other things, but okay? So look, seriously, if the unit circle is bothering you, come be healed. Okay, no charge. That was a dumb joke. Okay, so plug in pi over 2. Sorry, Zach, I didn't get back to you. You had a question.
What happened to the 1 in the numerator?
So I'm trying to find a way to pick something as u, so that when I take the derivative, my derivative is the other multiplying function. So I didn't pick 1 over sine of x because I know that derivative will be pretty messy. But if I pick this alone, the derivative is cosine. That's a really good fit. Because now when I start making my, does that help? 2 points. So look, pi over 2, simple. The top, sine is the up and down. So that's 1. Please.
So when you substitute cosines or sines, you don't just do what is in like the parentheses after, you do the whole thing. Like,
I'm not sure what that means.
I guess like when you were talking to us about u substitution, when you wrote up those like options, you had like cosine and then a something, but like, and then you had like e and then a something. So when you're doing like e, you do that something, but when it's cosine or sine, you put cosine and sine with it.
Incorrect. What I'm actually doing is I'm thinking of this as 1 over something.
Okay.
So the something I'm picking is the sine of
So the
x.
top one would be x.
If I were picking this one, you are correct. It would have been better to pick just x, but that doesn't help either. So it's kind of what I was telling you at the board. I'm kind of leaving behind that little structured approach and being a little more freewheeling, because Hadley's getting bored with the structured approach, so I'm trying to do it quicker. But yeah, I don't know, does that answer?
So you choose whether you use the whole denominator
can.
or whether you use the inside part, like we were talking about.
Yeah.
So whichever one just works.
Whichever one works.
Okay.
Now I can actually, Brennan, if it helps you, I can go back to the very structured approach and I can show you, even on the one you asked me about, how I can make the structured approach work.
Do you know what I'm talking about? Okay.
Like I can still make the structured thing work. Like you were talking about this one. You said we had, was it not this?
Yeah, and the square root one at the bottom as well. And I just didn't know if you substitute the whole denominator like it looks like, or
Stay with me.
Yeah.
So here's how I make my method that I taught you work perfectly. I first rewrite it. Now this is e to the something. So the u I would pick is still just the something.
Then it matches, okay.
The one that had the square root, I would have moved the root to the top. This isn't exactly what you had, but it's close. Like that.
Is there a way to move sine and cosines to the top?
You don't need to.
Because
I just look at it and say, this is just 1 over the something.
Okay.
Does that answer your question?
Yeah.
Point? Anybody else? Please, Rachel.
So I understand that sine pi over 2 is 1, but why are we doing that?
So everyone, please memorize 2 for Rachel. When you're doing an integral and you do a u substitution, you leave the world of x and enter the world of u and never go back. So it's a very narcissistic approach. That was a good joke. I think that was good. I'm sorry if you didn't get it, but that's an awesome joke. Did you understand the joke? That was a good joke. Like, I'm not apologizing for that one. That was good. If you're not laughing, that's your problem. So, seriously, you leave the world of x and enter the world of u. You never go back.
we'll need x to be pi over 2 and then x to be pi over 4 to finish that?
The reason we make the change is because they're going to give you about 4 problems on the AP test where 3 of them can actually be done 2 different ways. You can go from x to u back to x, but one of them is going to require the narcissistic approach.
Oh, okay. I see what we're doing now.
So we're just going to do the
We're
narcissistic
changing
approach.
the u's for the limits, right? Okay.
Good question. Don't stop asking. It's good work. Anybody? Cool. So I keep going here. So u must equal the sine. Now look, somebody in first period asked a question. I'm giving a full ticket for this one. Like every one of you can honestly tell me, like don't take it if you didn't honestly get it, but if you can honestly tell me the answer to this question, you can put down 10 points.
Can you give me some time?
You ready? You must answer it alone. Can't talk to each other. I'm changing the limits, right? Someone in first period, it's an honest question, but it shows clearly that they didn't understand what we're doing at all. They said, well, sometimes we do the cosine of the value? Like, why are we doing the sine of the value? Like, why am I doing sine of pi over 2? Why don't I do cosine of pi over 2? Like, to me, that clearly shows they're misunderstanding. They got to come get some help. They need to come be healed. Cambry.
Is it because when you said sin of x equals u and we're reading the x related to the u rows and the u?
Very good. This is the pathway. This is getting quite religious. This is the pathway. Right? This is the pathway. It's all on the video now. This is the pathway to the narcissistic world. It's the pathway to you. Right? You plug in the x value. Yeah, cosine has nothing to do with it. Cosine is not the path. It could be in some other problem. How many got it? Mark down 10. No way. You can thank first period for that one. Probably never use that question again. So we plug in pi over 4. It's very spiritual as hey today. Let's see, pi over 4 is right here. I have memorized. I've memorized, look. All the pi over 4 ones are always root 2 over 2. I'll write that down. Sine is the up and down. So I'd be going up, hence positives. So now I come over here. This is where we leave the world of x and enter the world of u. And we don't go back. Let's see, that would be 1 over u. Cosine x dx is du. Done. Well, it's done with the conversion from x to u. Questions? Please.
Sorry, the other unit circle it's square root of 3 over 2 and a half, right?
The other unit? Oh, yes, the values.
Those
Yeah,
are the other
you got it.
values. And square root of 3 over 2 is like the longer one, right?
Uh-huh.
Okay.
Perfect. The way I remember it, Brennan, if I forget, just make a quick list. Look at this pattern. Root, I guess I should put it here so the video can see it. I just say, oh yeah, unit circle is root 3 over 2, root 2 over 2, root 1 over 2. So, which one's bigger? Square root of 1 is just 1. Now we plug them in. Questions? Oh, we got to do the answer. Good. So this is my f prime right here. I need to find f. So f ends up being the natural log of the absolute value of u. Got to go between 1 and root 2 over 2. So this is f prime right here. I mean, this is f. Question? So now I say natural log. Absolute value of 1 is just 1. This is a positive number, so I don't need absolute value either. If that's the written portion of the AP test, I've just received full credit. I stop. Elijah?
So on the written portion of the test, if you have anything plusing or minusing, you don't need to change anything?
Correct.
But if it's timesing or dividing?
Multiplying, dividing, you can still leave it.
So where's the point where you keep on doing that?
This one you've got to do it because they want to make sure you know what that symbol means. If you have anything in the problem that says like f of 1, and there's a graph or something so you can go find f of 1, you got to do that. If there's any calculus remaining, you got to do that.
Just like simplifying, you don't need to do that?
Nope. That's because there's no such thing that really is simplifying. It doesn't exist. It's a nasty word. I don't like it at all. All you're doing is writing things in a different way. One person's, you'll understand this. One person's like, this is a better way to write it. It's like, no, it isn't. This is a better way to write it. Think about advertising. Like, if they're trying to convince you of something, they don't often say, 897 dentists out of 1,000 recommend this. They say 9 out of 10, because it's a better advertising slogan. But the data really was 897, you know what I mean? So simplifying is relative. It's just what you pick.
Okay.
Yeah. So I don't like that word. So I'm being very biased today. But I'd like to know why. Everybody good? Awesome. Hey, we're not going to do the multiple choice part of this, so just call it done. That part of your homework is completed. This problem was written in 1969. They pulled a few nasty tricks to get the multiple choice answer. I don't think you should stress about it. So
I was
the answer is
like,
natural log of root 2.
with like those LN things, like I was doing like number 5 and it had the same thing, like an LN minus an LN, and like I saw like could I make a flashcard that says like ln of x minus ln of y equals ln like of x divided by y.
Oh, true. So maybe it would be useful to kind of keep going.
Because like because like on number 5 I had like ln 10 and ln 5, and the answer is ln 2, and so like is that work for everything?
Yeah, that's true.
Is a question.
The nasty trick they did on this one is here's the nasty trick they pulled. We actually used this earlier in the year, so it's not brand new to you. Natural log of 1 is 0. Root 2 times root 2 is just 2.
How dare they?
How dare they? These two divide out. Then you're going to use Brennan's rule. Natural log of 2 things divided is the natural log of those 2 things subtracted. Natural log of 1 is 0.
That just went in a circle.
You're walking. You're going to give them the satisfaction of victory? Where are your guts, man? Where is your intestinal fortitude? If you don't quit, just move on to the next problem. Second, miss one, no big deal. There's no quitting. Question. Next one. Please write down number intestinal fortitude. You ever heard that phrase before? Apparently it came from my grandparents again. When my mother would get angry at someone, she'd call them a pot licker. Dirty pot licker. Made me ashamed to ever, lick the bowl after making frosting or something. Everyone have it written down?
On number 1, back on number 1. When you're supposed to out on the way, why isn't it negative?
Because negative times negative is positive.
I see.
When you distribute.
Distribution.
Distributive prosody. Principle. There you call it. Okay. Look. Okay. Does anyone need me to talk more about why one of the green formulas won't work? Okay, so let me demonstrate why U substitution. Oh, please. You good? Let me show why U substitution doesn't work. So again, you split it like we always do. Split it like we always do. So, the derivative of x squared minus 1 is 2x. That ain't 2x. Okay, question?
I thought it was, but it just had to have the same, like.
Has to have the exact same form. So, two problems. This is 1 over x plus 1. So that's pretty far away from 2x. Even if this were x plus 1, that still isn't 2x. All that can differ is the multiplier. So the derivative would be 2x, right? So if the other function had been 3x, that would have been okay. But not 3x plus 1. It can only differ by the multiplier. Well, I can actually get it to work if it looks like this. The biggest problem is the 1 over. The 1 over is the biggest problem. 2 for Avery. Anybody else? Solid. So let's see, if we choose this one, x plus 1, the derivative of x plus 1 is 1. That ain't 1, so. Okay, that means you've got to use the algebra trick. Shoot. With algebra tricks, I cannot teach you every possible algebra trick that they'll expect you to figure out. So you've got to be just a little bit brave and just kind of think of things and see if something will help. Please.
Can't you bring the x plus 1 to the top by times the by a power of -1?
So we could do this, 2 for Elijah. Trouble is, it still doesn't really help, because if I choose this as u, that's not this. The derivative of that isn't, so it's still dead end, but it was worth a try. It has helped in the past sometime.
Can't we factor the x squared minus 1 using the difference of squares?
That's the FFFFF rule. If you fail to factor, failure is finally in your future. So, not funny.
Funny.
There you go. The last part was decent. Not funny. I thought that was good. Terrible. Yeah, never mind. Whatever. Factoring does help. 2 for Maddie. Because now you can divide.
Oh my goodness. Whoa!
Whoa! Black magic.
The exponent on the outside?
No, so she's noticing that you have a difference of squares. So anytime you have a difference of squares, you just
She has to be on the outside.
like try it. What's x times x?
The answer.
X squared. You good now? Points for Hayden. Anybody else? Don't you dare say they cancel.
They equal 1.
They divide to make 1. For what x value do they... Oh, here's a genius question. Already gave away a full ticket. Yeah, what the heck? Can't talk to anybody. They divide to make 1. Always or just sometimes? Raise your hand if you know. These two divide, they don't cancel, they divide to make 1. Always or just sometimes. Sometimes being a bit of a loose phrase. Zach maybe understood that one. So they divide to make 1, always or sometimes. Lindsay.
Sometimes because if x equals -1, then it will be divided by 0. And that can't work.
They'd be undefined. So they actually divide to make 1 always, except, so I made the question a little bit clever. So they divide to make 1 always, except if x is -1. How many knew it? 10 points. Are we concerned about x equaling -1 in this problem? Why not?
Because it's not one of the limits.
Nice!
Yes, Hadley.
The limits go from 1 to 2. -1 is a place where we don't really care as far as this problem is concerned. Good work.
What if -1 was a limit?
They won't give it to you for our class.
Alright.
So it becomes a topic of more advanced thoughts. Is that okay?
Yeah.
Good question. We good there? Question? Okay. Now don't think too much. Just do the easy stuff. I've got to use the fundamental theorem. This is f prime. I need to find f. Two things being added. The antiderivative of x is just x squared over 2. The antiderivative of 1 is simply x. That's f. I need to find the value of f at 2 different x coordinates, 1 and 2.
Elijah, how do you get that the antiderivative of 1 equals x?
No worries. I'll talk with you and it will click, I promise. So I can't snap anymore after I broke my hand, sorry. That didn't work either. Dang, not loud enough. Still bad. That's better. What's the derivative of x? 1.
It just hurts.
So what would be the, you got it. Yeah. You're good. Please.
Can you just use like the power rule?
Sure.
And just like,
This is x to the 0 power.
okay, yeah. Makes sense.
Does that make sense? Yeah. Either way it works. The beauty of mathematical rules are they always work. Without fail. That's the beauty of math, of course, right? No exceptions, no, well, they're all, forget that word. Moving on. Are we good here? Please.
Why would you just use the expanded power rule?
Please remember, I thought I told you in class, but if I forgot, I apologize, that we don't want to use the expanded power rule if n is equal to positive 1. It's not illegal, just unhelpful. The other way is quicker and easier. Got it? Anybody else? My finger hurts now. Don't do that too often. So expanded rule, can't use it when x is -1 because you get undefined. Sorry, n is -1. Because you plug in -1, you get undefined. But if it's 1, it's just not helpful, so I don't recommend it. It's not wrong. You guys remind me of my first Brazilian companion. Walk down the street. Can't do it yet. Can't do it yet. Like day after day. Like, gotta loosen up, dude. Gotta loosen up. We good to hear? Very nice.
It just hurts. It just hurts.
So here, let me tell you the secret. Then we got to do the next problem. Look.
Stop. This red What's the dad?
Stop. The secret is, it's like apparently all of us could actually move our ear if we could just, yeah. Oh, James can do it really well. But the secret is you have to train your brain to tell it to relax this muscle. Like it's got to be where your muscle goes completely limp, like the muscles up in your arm or whatever, right? It has to go completely limp so that when you go like this, it's just slapping them together.
But this side is like, it doesn't go limp. It doesn't. This finger like is like rigid.
That's like fire
Quiet. We got 2 more problems we got to do. Look.
You have bigger problems sitting here.
Yes. I'll let you finish that at home. Now it's just arithmetic. So, next one. Please write down number 8. Please write down number 8. Okay, please note, the expanded power rule will not work.
Because it's squared.
Because it's squared. Power rule, the expanded power rule does not work because it's x squared. You need me to talk more about that? Okay, oh please. So if you look at the rule, the expanded power rule, it only allows for ax plus b. A being some constant, b being some constant.
Oh, the x is squared.
Right, so the squared here, my bad, Hayden. So the squared, you're totally good. So the squared here is causing the problem. Squared here. Question? Awesome. Use substitution. I do have 2 things multiplied, but it doesn't help because if I take, yeah, it's not going to work.
This is the plus one.
So you've got to think of something algebraic.
Couldn't you do 2? Couldn't? Yeah.
Whatever.
Couldn't you split them up into 2 if they're multiplying?
Oh, never.
Oh, it's only if they're adding.
Yeah, only if they're adding. Good question. 2 points. Yeah, never split them up cross multiplication or division. So you got to think of an algebra trick. Avery.
Isn't it like the same thing I understand where you can do x plus 1 and x minus 1?
Oh, if it's plus, they don't factor. No worries. Plus factoring not so helpful because we don't have anything to divide with. So it only factors with complex numbers if it's plus. We don't do complex for our class. So, Elijah?
Could you just do the power rule? No, because you can't, because it just has to be an x.
Correct. Good question. Figure you can miss a few, it's all right, and go to the next one. Good work. Okay. Seriously. The algebra trick is to use the Allison's distributive property. So multiply it out. Sneaky. Sly dogs. Pot lickers. Pot sticker. You dirty pot sticker. Question.
Oh, now they're all adding.
Yes, nicely done. Yeah, please memorize what Hadley just observed. Hey, please memorize what Hadley just observed. One key thing you're doing when you're doing an algebra trick is you are often simply trying to change from multiplication to addition. If he needs me to say it again, wait. Okay, very good.
Can we call that the Hadley trick now?
Yes, I need a sign.
I need.
Pictures are appreciated because then it's easier to remember you amongst the thousands of students I've had. So. Yeah, the wall of honor is always open. There's lots of space. So. It's got to be nice, you know, to put up junk. So it's got to be nice. Just trying to think of something that goes better with Hadley. And next problem. Please write down number.
Wait, so the 1
Yes.
goes to x. Can I think of it as like 0x plus 1?
If you like the rule, it would be this one. What is x to the 0? It's 1. Yeah, anything to the 0 power is 1. So x to the 0 is 1.
Because okay, you're thinking about it like backwards. Does that
I don't know,
mean,
whatever
like,
works.
okay, yeah. But he's thinking of like the derivative of it.
Please write down
I
number
I do.
9. Go, come on. We got 5 minutes. Write down number 9. Come on. Write down number 9. Okay, here we go. There's no rule, but if you can remember derivatives, there's a nice choice for you. If you look at your blue rule sheet, you will remember that the derivative of the tangent of x is 1 over the cosine squared.
That's satisfying.
So this one works beautifully. So I have to change the limits. Tangent is the same thing as sine over cosine. So sine of pi over 4 divided by cosine of pi over 4. Think of the circle. Pi over 4 is here. So the sine is up, the cosine is over. So they're both root 2 over 2. They're both positive. So that's 1.
Can you explain the red part?
So it's a unit circle problem. So what I remember is you okay that tangent is sine over cosine? So I draw my circle. Or try again to draw my circle. Okay. Pi over 4 is right there. Sine is the up and down. So sine is going to be root 2 over 2. Cosine is the back and forth. It's the x-coordinate, so it's the same, it's positive. That's 1.
And you do the same for 0.
Now you go for 0. Get a little more space here. So u is equal to sine of 0 divided by cosine of 0. So here's angle 0. Sine is the up and down, or the y-coordinate. The y-coordinate right there is 0. The x-coordinate is 1. So now I have my new problem over here. I'm going from 0 to 1, and I'm going to do, let's see, e to the u, du.
Is our notations wrong if we don't put those limits until we do the bar?
Say again.
Like I put the u limits like once I move to the bar. Once I
Yeah, do it earlier, otherwise
Do it earlier.
you'll have
When
trouble
you
on
put
it.
it-
Do it earlier.
do it on the step that you put in the u.
Okay. There we go. So you find the antiderivative, which in this case is simply e to the u. Had these happy place, but then it kind of sounds confusing.
So then, like, on like 10 and 11, it has x and e as the limits. You just plug those in, like, when you get to the end as well. Like, that won't like, be an issue.
Yeah, this one's not used up well.
Like, doing e, like, how do you do the e in your head? Or does it, I guess it stays with e because the answer has
Just, they're on terms.
You just plug it in.
They give you some weird